able to represent the signals that you see. Okay, the signals are basically speech signals. Okay, so if linear prediction model for speech, it follows a very basic assumptions and approximation to say, okay, a speech sample at time t can be approximately by a linear combination of past signal samples. Okay, very simple, right? And any point here is some linear combination of the past. Okay. So the reason behind this, okay, you can imagine, right? If you have a point, that can be a linear summation of the past. That means there's a certain local correlational structure with new signal, which also makes sense because when you speak, every point of that signal versus the frame that you just previously have, okay, those needs to have some relationship. Okay, it doesn't every single point of this is not going to be it's not going to be independent. Okay, because the way we speak is flowing out of my mouth, constructing a sound. So the idea is very simple. A speech sample at time t can be approximated by a linear combination of the past signal samples, and we'll see because of this kind of assumption and basic idea, it actually is quite a good model for speech signal. Okay. It's our relationship to the source and filter model. Okay, we'll see also as we talk about linear prediction model. Linear prediction provides we call the robust and reliable estimate of the filter. Okay, part of the source and filter model. Okay. So people use linear prediction model as a way to estimate pitch. Okay. Foreman is basically the filter part, pitch is the source part. Okay. And then a lot of applications of using linear prediction originally they exist in terms of speech coding, okay, compression. Okay. Imagine if you have a mathematical models of a speech signal like this, basically you're rewriting the signal as a set of parameters. Okay. So now if you want to reconstruct this signal, you can just only record those parameters. Okay. So it becomes a coding process. Okay. Make things you use fewer bits to actually represent the entire speech signal. Right? So the mathematical approaches help us to do kind of compression, speech coding. So if you don't know, right, when you speak on the cell phone, right, when you talk on the landline, okay, the signal that's being reconstructed on the other side, they don't send this thing over. Okay, they don't send the actual time waveform over the cell phone line or the landline. They send some representation, some code of this thing to the other side of the receiver and then reconstruct, and you hear the sound of this person. So if you ever hear yourself in a cell phone, or you hear yourself in a landline, okay, you find yourself voice a bit differently, okay, because basically we code up our speech signal in a different manner and send it over through a communication line and then reconstruct. Okay, so that mathematical process called speech coding. And then later we'll see this linear prediction model also being used as some speech recognition front end. Okay. So let's continue. Okay. So linear prediction model, very simple. It's run on a simple hypothesis. Using linear prediction to explain most of the information in speech signal in this particular form. Right? S of n, right, the speech signal at particular index n, right, is a summation, a linear summation of the past samples. Okay, so it's your choice, right? Past p samples. Okay, with some coefficients a1 to ap. Okay, multiplied by the past samples with some error term, or we call the rest of the term u of n, or some leftover term. Okay, so want to make sure this a of k, okay, this linear prediction signal explain what's the majority part of the Sn. Okay, this will be as minimum as possible because the majority of the information in your speech signal hopefully can be done by using this linear past prediction. Okay, so again, we want to make sure that the idea is that S of n equals a linear combinations of the past p samples plus some small error term, and hopefully that error term can be very simple in terms of speech. If it's a voice sound, hopefully that u of n is either an impulse track, or if it's an unvoiced sound, hopefully it's looking like a white noise. Okay, so you can see that this is like a filter part of it. Okay, so if we have this formulation, what is the linear predictive signal or linear prediction signal? Okay, so that's S delta of n to be the actual linear predictive signal at n using the past p sample, right? So basically it's just this sum of k from 1 to p, S of k is n minus k, right? So this is once we know alpha sub k, right, we can actually generate a prediction. Okay, so every time at a particular S of n, okay, we can use A sub k, okay, sum of the past sample to predict what's the next one. Okay, so let's go linear prediction, linear predicted signal. Okay. Okay, so let's take a step back. Okay, look at it from a system and signal perspective, right? So we know S of n, right, equals to, right, some linear predicted signal, right, sum from 1 to p, right, p past samples. Okay, a sub k is some constant terms, a n minus p plus some input. Okay, this is a discrete signals systems, right? Let's turn them into a z transform. Okay, so S of z. Okay, and similarly, this is a linear combination. So a linear shift in the original time domain equals to z to the minus k in the z domain, right? So this is z transform in case you forget. Okay, so it's a very similar stuff. Z is pretty much like Fourier transform, right? Fourier transform is the transform around unit circle. Z transform is the transform around the entire complex plane. So the z transform evaluated on unit circle is the Fourier transform. Okay, in case you forget that. Okay, that's on the side. But anyway, so let's take this time domain into z domain. Okay, sum from k from 1 to p a sub k is c z minus k plus the input, or we call error term, u of z. Okay, let's do some massage equation. S of z minus linear predicted signal equals u of z. Okay, so we can pull out S of z. You have S of z multiplied by this thing equals this thing, right? So original signal spectrum multiplied by a certain filter, okay, or a certain z transform equals the original input. Okay, so S of z, right, okay, can be obtained and equals to u of z times h of z, right? If you move this term over here, okay, so S of z, the signals z transform or signal spectrum equals to h of z multiplied by u of z, okay, equals what's this h of z? Is basically this entire form, move it into the denominator, right? So 1 over a m of z, is we shorten it as a m of z, okay, times the input, okay, u of z, okay, where a of z is basically this term. Okay, so h of z equals s of z equal divided by u of z, so where h of z essentially is this particular one. Okay, so in this particular linear prediction model, the explicit parameters we need to have is gain, okay, the energy of the signal, okay, overall, and these alpha coefficients. Okay, like think about all is z sub z minus k, right? Every z minus 1 minus 2, that means the signal get delayed, right? Every delayed multiplied by some alpha. Okay, we need this coefficient, okay, to be able to do the linear prediction model. Okay, so there's some model parameters that's explicit, which is g and a. And then implicit here, we're saying if we're able to get this right, maybe the implicit u of z, okay, or u of n, either to be the sum of delta function, where impulse strength or white noise. Okay. In this kind of model, in this kind of model, okay, we call this O-pole model of speech signal, because look at this one, right? 1 minus summation of some terms with z to the 1 minus 1 minus 2. This is our like polynomials, right? You can do some factorization, okay, into a product. Okay, so all the z's that would equal to 0 happen in the denominator. Okay, so this is a pole location, right? There's a pole location in your z plane where at those location it's going to shoot up a spike in your spectrum. Okay, right? So there's no terms in the numerator, so this is not a there's no feedback. Okay, so everything happens in the past. All the things, this filter only depends on its input. It doesn't depend on output. Okay, so this kind of model is called O-pole model. So these are interchangeable terms, right? So linear prediction model is a way we start hypothesizing, okay, the speech signal in time domain at this particular time frame, okay, equals a summation of the past p samples with a linear weighting. Okay, look at that from a system and a signal perspective. Turn them into a system and signal perspective. You have the signal essentially equals this thing multiplied by this thing, the z transform. What that means, right? This is source, this is filter, equals your output, which is your signal. Okay. Now we're just saying this. We don't know what this u of z is, but we're saying this h of z is, is 1 over this sum over g over 1 minus sum from k from 1 to p alpha k z z minus k. Okay. So we're saying this is the filter function, and by hopefully optimizing how we get a, okay, the rest of this u of z can be very simple. Okay, it'll be either white noise or impulse strength. Okay, so we want to make sure we explicitly optimize for trying to find out what alpha k's are. And then by finding what alpha k's are, hopefully we explain most of the information within our signal, and then leave the rest errors into the U of Z. Okay, you complete the entire system perspective. Okay, so that's another way to understand linear prediction modeling. All right, so we stop here for a second, and then again terminology. Right, so this A of Z, right, equals to input divided by divided by the output, which is actually the speed signal spectrum. This is the input spectrum, right, equals 1 minus sum from k from 1 to p alpha k c k. We have two different terms we can call this. Okay, one is called inverse filter, right? By applying AZ to your S of Z, right? AZ multiplied by S of Z, what you get the source, right? So at the output multiplied by AZ, you get the source. So that's what we call, one way we can think about this A of Z is an inverse filter. By looking at your output, okay, multiplied by a filter, then you get your input, okay, inverse filter. Okay. Another thing we can also call this thing A of Z is the prediction error filter. Okay, we'll talk about that as well. Okay, but anyways, think about this entire process, right? First, we start very simple. A frame is going to be approximated by the summation of the past p frames. Okay. The reason, intuitively, you can imagine, right, because the signal has some correlation over time. Because we're speech, right, coming out in sequence, okay, in series, it cannot be every point has nothing to do with the past samples. All those things are correlated. So mathematical engineers say, okay, let's approximate that. Say, okay, a signal is going to be linear sum over the past p sample. Now, once you write that mathematical formulation, then you say, okay, let's try to understand this mathematical formulation of input-output relationship, rewrite that into a system and signals perspective, and you'll see that basically, by doing that, we're essentially trying to find this A of Z, okay, which is our filter function, okay, and there's some U of Z, which is the input function, okay, and then those two multiply become the output, which is the speech output. Okay. Now, we haven't talked about how do we actually find this alpha. Okay, we're just saying, okay, if there's an alpha, okay, then we can do this. Then we start thinking about this whole system and perspective. Okay, so keep this terminology in mind. Wrap your head around this. Okay. Now let's think about how we actually get those coefficients, right? So we already know a speed sample is going to be linearly combination from the past p samples, okay? Each one with the constant A, okay? So let's say, okay, let's try to do one thing. First, this is a linear predicted signal, S delta n, right? So basically it's just a summation of what I think would be predicted, okay? This is the actual signal, okay? The difference between the two is the error signal, right? So the one I think is going to be predicted and the actual thing I see. Okay, the difference between them is the error. Okay, so error signal is S of n minus sum from k from 1 to p alpha sub k S n minus k. Okay, so we want error to be small, right? Because we want almost all the information are going to be in here, okay, to fully represent this thing. Okay, so we want this error to be small, okay, to be as minimal as possible. Okay, so what aspect of this error signal we want it to be minimized? So what aspect of this error signal in this linear prediction model we say let's minimize the short time the energy of this short time error signal. Okay. So the difference between what I think is being predicted and what is actually the data it is, okay, the difference between them is the error. I want to make sure I find a set of alpha so that the short time energy of this particular error signal is minimized. Okay, so by doing this optimization, you can ensure, okay, most of the information are going to be captured by this S delta event. Okay, so if we're able to solve this optimization problem, then we're able to find those alpha. Then we're make sure in a way when we choose those alpha, the error signal will have the most smallest error in turn, and the error signal will have the most smallest energy, okay, within that signal. Okay. So I write it, okay, energy of the error signal, okay, sum from n to infinity, E n squared, right, of n, right, so sum over all n, okay, S of n, right, particular frames, at that index minus S delta n to the square, okay. Expand that, right, energy in the error signal, sum over all points within that frame, Sn of m, and this is the linear predicted signal, right, the difference between the two, right, sum from k from 1 to p alpha sub k, Sn n minus k, right? So the shifted signal, each one multiplied by alpha sum dot is what we think is the predicted signal. This is what the true signal is. Sum over all those samples of that particular frame. Okay, now look at this square. Hopefully we can minimize this with respect to alphas. Okay, we can minimize this with respect to alphas, then we can find a set of alphas that this whole term goes to as small as possible. Okay, so that's a basic idea. Of course, we'll talk about how to solve it in a more of a quick, intuitive way, but understand the basic concept first. Okay, you have linear predicted signal. Okay, our goal, right, as engineers, our goal is to make sure that linear predicted signal has the most information. Okay, how do we ensure it has the most information? Let's look at the error between the actual signal and what I think is being predicted the signal. I want to make sure the difference between them of their energy is minimal. Okay, using that criterion as a way to find the alpha in my coefficient. Okay, so that's basically the process of nowadays the terminology called learning. Okay, back in the days it's just estimation. Okay, estimating what that alpha needs to be so that it can basically get this equation right. Okay, so finding a minimum with respect to alphas. Okay, again. The general concept for everything, okay, DE, right, DA, because now you have a error function, right? You have a function, right? You have a function like this, okay, you want to find the parameters such that this thing goes to global minimum. How do you do that? You take derivatives, okay, set equals 0, and solve what that alpha needs to be. Okay, that's very simple. Finding a minimum of a function is by taking a derivative, set it, reflect to that parameter, set equal to 0, okay? So, and that's why a lot of times you see the things we want to optimize always have this energy term in here because it makes the differentiation easy. Okay, you just bring down this 2 in the front. Okay. All right. So I skip a lot of derivation, but again, you're eventually yield this equation. Okay, sum over all m samples, right? A particular frame n minus I Sn n. Sum over k. K from 1 to p pass samples, each one has a coefficient alpha sub k. Sum over m samples, Sn n minus I, Sn n minus k, okay, for I goes from range 1 to p, okay. Looking complicated equation, let's redefine a few terms so that the equation looks a bit easier to handle. Let's define a term, phi n, right, index the frame, ik index, this I or this k, okay, basically the shift position, okay, where you're shifting I position or shifting k position. So this phi n I k equals to sum over all samples within the frame, Sn n minus I, Sn n minus k. Okay, and this is basically phi n I 0 because then there's no shift in the second position, right? So phi n is basically just some if you take this thing, okay, then it's sum from k from 1 to p alpha sub k. Basically rewrite this. Sorry, once we define this term, we can rewrite this equation into phi n I 0 equals to sum from k from 1 to p alpha sub k multiplied by phi n I k. Right. So you have this thing that equals to a p linear equations, right? Okay. So you have p coefficient that you need to solve. So you have p coefficients, that p coefficient that you solve, right? The alpha k from 1 to p, then k also from 1 to p, phi n I 0, right? It gives you a set of 9 equations that you can actually try to solve for alpha. Okay, let's try to solve it now. Okay, so we know this, right? Again, rewrite, again, repeat. This is the equation that we take d alpha sub I is equals 0 and try to solve. We get sum over n samples, Sn n minus I, Sn n, right? This is the original signal at the frame n, moved to I point, multiplied by the original signal at n point, okay. Sum from k from 1 to p, right? All past p samples, sum alpha k, right? Sum over all the frames, okay, the points in the frame, Sn n minus I, shift your signal, I points, okay, shift your signal k points for all I that's gonna be shifted between 1 to p, okay, right? So that's, then we can write this thing as phi n I 0, sum from k from 1 to p, alpha sub k, phi n I k, I from 1 to p. So you have this set of p linear equations. What you can do is first compute phi n I k for I from 1 to k, and k from 0 to p, okay. right? So again, repeat, you can first compute all the phi n I k, right? So all the phi n I k for I from 1 to p and also k from 1 to p, you can get all the phi n's because there's only numbers are generating from this phi n I k, right? So you just need to loop through all the I, loop through all the k. So what's loop through all the I? Basically shifting your signal, right? Shifting every I points, okay? Also the other signal shifting every k points. All this combination will give you a value of phi n I k, right? So once you compute this phi n I k for all I, for all k, okay, then you have all the values that are needed because these are become the number you can compute, right? Phi n I0 is just Sn n minus I times Sn with no shift. So you have signal that's no shift, the other one shifted around, okay? And here is just one shift here, another shift here, another shift, okay, I shift again, I shift 1 point, and then 1 point, right? So basically you're just doing, once your signal either don't shift the other k points, meaning p points, shift your original signal once, shift p points, shift another signal once, okay, shift k points, right? So you get all this combination, you can fill up this thing, okay? Once you fill up this thing, then you can actually back solve it, okay? So we'll show some methods to actually solve this. So it's basically a summation over n, okay? Again, the summation over n depends on the windowing function that we choose, okay? That summation may, again, back here, right? The S of n is the signal that you actually get, okay, directly from a signal, or you do apply windowing function on it. That's a different story. But if you apply Hamming window, if you apply anything, you have to make sure the signal is not just shifting and multiply. It may be shift multiplied by the weighting of the windowing function, then you sum. Okay, so because this is S sub n, this is a short frame of that particular signal. When we call it short frame, you have a signal applying a windowing function. Okay, so you have this summation over these two shifted short segments of window, and then sum all those things up to the shift of p points. Then you fill up all these phi n I0. You can solve this equation. Okay, that's repeat the so the minimized error. Okay, you can plug all this in, right? Once you figure out all this, is minimized error is phi n00 minus sum from k from 1 to p, the alpha sub k phi n0 k. Okay, this is when you figure out the alpha sub k, then you can compute the minimized error. Okay, so there are two ways. Okay, we can think about computing this stuff. Okay, now first, this Sn of n, right? Sn of n, right? All these things, Sn of n, Sn of n, Sn of n. This is, we call it short window of a segment. Okay, right? So a short window segment of the original signal. Okay. So one first way we can think about this is, okay, assume Sn of n, okay, is obtained by windowing using a finite length sequence. Okay, so Sn of n, okay, equals to Sn plus n multiplied by Wn, right? That's the windowing operation on the original signal. Okay, so it'll be 0 outside of 0 to n minus 1. Okay, so you can kind of imagine a prediction error can only be non-zero. Okay, for n that's between 0 to n minus 1 plus p. Okay, because and this error signal, when you say, okay, I'm gonna take a signal out. Okay, I'm gonna try to do linear prediction. Okay, because you're doing a past p sample to predict the current samples. Once you segment a window, right, the first sample is gonna be predicting from zeros, right, from zeros to that sample. So you're gonna have a large error. Okay, because you segment out the signal, right? So it's not, you're not segmenting out. We take a segment out of the signal. Okay, then we start to doing linear prediction model. Okay. When we do a linear prediction, we have to assume, okay, you know that, okay, because once you take a segment out, everything else here is 0. So you want to predict this point, okay, using the past p samples. All the samples are 0. Okay, so you're going to have an error signal that's going to be quite large at the beginning. Okay, and the error signal can only here be error prediction error can be it should be 0. Okay, so only within the period. Okay, here when it actually has some values, can predict it on. Okay, otherwise once it's being outside, there's no values. So the error signal will only have value from n to 0 to n plus p minus 1. Okay, everything else is 0 predicting 0. Okay, 0 predicting 0, and that error signal is non-existent. Okay, so this error energy signal, once you do a short time window on your original signal, there'll be large at the beginning. Okay, the first P samples are predicting from zeros, and the end, right after NP samples, you're predicting zeros from non-zeros. Okay, right. So that's called the first method called autocorrelation method. You take the signal out, okay, one segment out, then you do all that computation to find the alphas. Okay, again, repeat, right? Phi nik is that particular form, okay? So phi nik, right, sum from 0 to n minus p, Sn n minus I, Sn m minus k. So let's do a substitution, n prime equals to n minus I. We can rewrite that as phi nik, n prime equals 0 to n minus 1 minus I minus k, okay? Sn n prime, Sn n prime plus I minus k, okay? So let's look at this form, okay? Let's rethink about the autocorrelation function that we just learned. Autocorrelation function Rn of k equals to summation of n from 0 to n minus 1 minus k, okay? Xn plus n, w prime m, by xn plus n plus k, w prime k plus n, okay? If you do this, you see that this is essentially the Sn of n, okay? This is Sn n plus k. You have the same summational term here and here, okay? So now we can rewrite this phi n of ik, okay, essentially equals to Rn, the short-term autocorrelation function of that particular frame. The lag is I minus k, okay. So again, this and because this is index, let's put an absolute value around it. Okay, so there's always positive integers. Okay, so one is here, one is here. That minus that, there's a distance here. This minus that should have the same distance, so they're symmetric. Okay, this should be a absolute value here. So we again rewrite the original this normalized equation that I'm trying to solve for linear prediction coefficient now becomes sum from k from 1 is p, okay, some coefficient outside of k. Now it's multiplied by the autocorrelation function Rn, right, I minus k, absolute value, okay, index that equals to autocorrelation function Rn of I. Okay, so we rewrite the original equation that tried to solve the normalized equation of the LPC now becomes a process of computing autocorrelation function. Okay, once you have the autocorrelation function, then you can put it in here and can solve it. So so you don't have to do this shifting. Okay, so essentially what you try to do is do this autocorrelation function. So this minimum mean square error, you can plug it in. It becomes Rn of 0 minus summation of k from 1 to p alpha sub k Rn of k. Okay, now we can write this entire thing as a as a linear algebra matrix form. Okay, Rn of 0 to Rn of p minus p minus 1. Rn of 0 to Rn of p minus 1. Okay, Rn of p minus 1 times 2 p minus 3 to Rn of 0. Okay, so this is a p by p matrix R times the alpha coefficient, okay, equals to Rn1, Rn2, Rn3 to Rn of p. Right? Basically, it's the rewriting of this equation, right? So this summational form in this formula, you can rewrite as matrix form, okay? So some coefficient multiplied by Rn I minus k, okay, for every alpha k, right, multiplied by Rn I minus k, because this is I minus k is absolute value around it, so you have this is the same thing as this, right? Because I minus k, one of them is originally is minus 2, but none of them minus 2 is just 2. Okay, 2. So this entire matrix, right, is 0 on the side, 0, 1, 2, 3, 4, 5, up to the p. Then you have 1, 0, then 1, 1, 0, 3, and so on. So and it's 0, 1, 2, 3, up to here. Okay. So this matrix, we call this a Toeplitz metric. Okay. There's a way to solve this p sets of equations, okay, obtaining p coefficient really fast using recursive formula. Okay, that recursive formula we call the Vincent-Gurry recursion. Okay, we'll talk about it a little bit, but again, that's not the main purpose of this thing. Okay, but understand this whole process. Okay, create linear prediction model. Okay, assuming a speech sample as being approximately bypass p samples. Okay, now. That alpha coefficient we don't know because we don't know how much of it will add from the previous samples. Okay, we want to find those alpha. How do we find? Okay, we want to find the error signal, that difference between the two, and and you try to solve for alpha with respect to that error signal. Okay, but in practice, right, you're not doing the entire speech signal, right? You're taking a short segment, okay? You're doing a short segment and then to LPC, short segment into LPC, short segment into LPC, okay? That short segment into LPC, okay? So if you say, okay, what I think I'll do is take a short segment of the speech signal, okay, applying windowing function on this, and then do LPC or that whole business, okay? That boils down to basically running short-time autocorrelation function on that short segment of window, okay? So you can compute this autocorrelation function, fill up this matrix, okay? These are unknowns, this already know, so all the things that you know that you just need to solve. But how do I solve this, right? Usual matrix inversion takes a very long time, okay? Now, the reverse inversion is just a fast way of solving an inverse of a matrix when your matrix has a particular shape, okay? So here comes a little bit of linear algebra, okay? We're not going to go into detail of linear algebra, but there's some tricks that, there's speech people that use from linear algebra. So if I know the matrix in that particular form, I can design a fast way of solving this. Because why? Because, imagine you're running a speech signal that comes in, you want to call it up as this kind of alpha coefficients, right? We were saying one of the applications is a speech coding and transmission, okay? If I can find a set of models and set of parameters that represent well the signals, now you have a speech segment that comes in, all I need is these alphas. I can send alpha, I don't need to send actual timestamps, okay? Those time values, okay? These should be computed very fast, okay? Once it's computed, send that. Once it's computed, send that, okay? Computed, send that. It doesn't send that whole 44.1 kilohertz sample over the lane line. So these are the things that's being computed and sent it, okay? And the process of doing that is doing, a time signal that comes in, right? You can imagine the way you write C code, right? You have two signals and then you encode the addresses and start to do dot product, right? That process can be very fast. So autocorrelation is a dot product process by shifting the buffer and then dot product, and then you compute these values and you send it to a recursion formula and finally get this alpha sending over the other side. Okay, how do they reconstruct? They just predict it, right? So you have the coefficient and then they can reconstruct the actual original signal by giving the proper input, right? So if the input is an impulse train or the input is a white noise, then you can reconstruct the signal at the other side, then the voice comes up. So that's sort of the entire process of thinking about linear prediction. So here's a sort of a pseudocode for Leibniz-Sandurban equation. So really what you're trying to get at is this R matrix multiplied by the alpha coefficient equals to some R, right? So we want to find alpha equals some R inverse of R. So I think it's easy, probably just go look through this. This is our pseudocode. Okay, we won't go into details of deriving them. Okay, but have time to look at it. If you fire up a linear prediction model in your toolbox, okay, there's a method called Leibniz-Sandurban to solve it. Internally, they're running this. Okay, so we'll skip that part for the time being, but take a look at it. Okay. Now I wanna next thing I wanna talk is this thing. Okay, so the autocorrelation method let us find a way to solve this equation, and then we'll continue on next time. Okay, but I want to do a prelude. Okay, this is by assuming let's take a signal and do a framing. Then we start doing linear prediction model. Okay. Now another way to think about doing linear prediction model is say, okay, let's take a segment of the error signal. Okay, so this is different stuff. Okay, we take a segment of the speech signal and then do autocorrelation. Okay, but the problem is that like we did with the autocorrelation function, once you shift it outside, okay, you're multiplying things that are zero. Okay, now if you take a segment of your error signal and start there, okay, then you don't have this problem of as you're shifting these values, they get weird behavior at the boundaries. Okay, that's a problem where you take a signal perspective, let's take a segment of the signal, start shifting it. As you shift it outside of the other thing, it gets zero behavior. Okay, but if I take a segment of an error signal, okay, then it's more fixed. Okay, it's work on the error signal. But what that means you're taking two sets of signals that could be of different length. Okay, and if you recall back when we talk about autocorrelation function, there is a modified autocorrelation function. It's a very similar idea. Okay, modified autocorrelation function says, okay, to make sure I don't have these issues of as I slide my signal outside of the range of the other signal, it gets 0 here. Okay, so I want to pad the little values here, so that I always have values across the range. Okay, same thing with this kind of method. Okay, we can also think about, okay, instead of taking a segment of the speech signal and start to do all this sliding and then trying to find the final value, you can say, okay, let's take a segment of the error signal. I still do a lot of sliding, okay, but you're not really doing a true autocorrelation kind of thing. Okay, we'll talk about that as another method, okay, to solve linear prediction model. Okay, that method also will boil down to a certain kind of a matrix form like this. Okay, and that matrix form is not a matrix. It's another symmetric matrix. Symmetric matrix also it gives you there are fast way to solve it, but not as fast as Toeplitz metric. Okay, Toeplitz metric, the computational complexity is only p to the square. That's very good. Okay, usually p is, we'll talk about it. Usually p is not very large, okay, 15, 20 or so. Okay. Square is 400. That's nothing. Okay, but if you have the other set of version, it can go to I think cube or something. Okay. But it's still faster than standard inverse. Okay, but there are different ways of solving the same equations. Okay, the same concept. So when you do linear prediction model, okay, it depends on you're interested in solving it fast. Okay, but understanding there's some problem as you do short time segment of your window sequence that will have odd behavior at the boundary. Okay, the problem of all this short time processing, right, is the odd behavior at the boundary. Okay, as you start to do autocorrelation function and start to do things on the boundary, just because those things outside of the range is 0. Okay, but you have to do that because we're taking a small segment, assuming that segment is stationary, so that we can do all the analysis, all the prediction model there. So again, this is a trade-off, okay, of always speed processing, and always when you see different methodology to talk about that short-term processing changes the way people again do all this sort of a mathematical derivation. So again, I'll stop very soon. Next time I'll talk the other versions of this normalized linear equation to solve for alpha p coefficient. And what more important, I think I'll talk about again in the linear prediction model. You'll see this. Sorry. Right. This is H. Right. H is this filter. Right? So you can actually look at the frequency response of this filter. Okay, and you'll kind of see, okay, what those alpha coefficients essentially help you to do. Okay, and then we'll see a plot by doing this. Okay. By properly learning all these alpha k's, okay, this filter response, okay, will align properly, okay, to the formant structures of the speech signal. Okay, so this is important. By solving is a little bit like, I feel sometimes when I talk about it, I feel a little bit like magic, right? You start by saying, I just want to have a linear prediction signal. Okay, how do I get it? It's so intuitive. Okay, find the linear combination of past p samples. Okay. Now what you do is try to solve it. So intuitively you say, okay, well, the thing I guess it to be in the real thing, let's take the difference in energy of that. Okay, solve it. Okay, once you solve it, you get a set of coefficients. Look at it from a system perspective. Then you're designing a filter already. You're designing a filter of g minus 1k from 1 to t alpha k. This is some polynomials, right? You can rewrite that as product of poles, right? You can write that as product of poles in all the z in z space, basically. Then you evaluate around the e to the j omega circle. Then you can see, okay, at which position you'll have a peak, because at those positions, set them equal to 0, this thing blows up, right? So that means there's a peak there. Okay, so you can look at this filter response, and you look at, okay, now of this particular short segment of speech signal, the filter I'm trying to model at is there's some shape there. Okay, that shape, if you look at closely, it closely relates to how the human formant structure is. Okay, so and then that's also by definition. Okay, we'll see that next time. That's by definition it's going to happen that way, because the way we analyze we use the error of the energy. Okay, the error. Sorry, we realize the energy of the error signal. You minimize this thing. Okay, when you minimize this thing, right? Think about the error, right? So what's error? So whatever is left is error, right? So this divided by this, we can call this input or we can call this error, right? Because whatever is left is not included here. This is the signal. This is what you model. Whatever is left here, we call it either input or we call it error. Okay. So by moving this over here, when we try to minimize the energy of this thing, okay, we're minimizing a ratio of energy between this and this. Okay, when you're minimizing a ratio between energy between this and this, okay, so you have a spectrum here. You're trying to learn a spectrum that matches that spectrum in a way that matches their energy spectrum. So it's gonna try to model your original signal. If it has all this peak, it's gonna try to match that, because by matching that, the ratio between this and this will be smallest. That'll make this error the smallest. Okay, so we'll talk about that entire frequency interpretations of looking at this filter. Okay, so again, wrap your head around this. So it's hopefully we're building on this course. Okay, it's going to continue to build. Okay, so from the basic, right, source filter model, okay, short-time processing. Okay, that windowing really kicks in, right, in a way that you probably haven't imagined. Okay, so it really kicks in when we do all this core autocorrector function, when we compute this, change the frequency interpretation, right? Looking at the frequency analysis, now we're saying we're proposing a model to model this thing. Okay, looking at it from a system perspective, looking at it from a learning perspective, trying to find alpha, and finally looking from a speech perspective, that you're actually trying to model that format. Okay, so again, this is building on. So a suggestion I like to say, if you feel a little bit lost, again, quickly go back to, because things will continue to build and quickly build. Okay, so LPC, the next thing we'll talk about is a capsule analysis. The next thing we'll talk about is LPC with capsule analysis. Okay, so, and then we'll talk about male scale. Then we talk about male scale capsule analysis. Okay, then we're done with the speech analysis part. But this thing have to keep in mind, these are tied together. You have to basically be able to interpret all these things in a line. Okay, we'll talk about that next time. More in details. Again, repeat, this linear bridge transfer is important. Okay, has been around at least for tens of couple years already. Okay, so it actually provides a very nice mathematical ways of modeling a speech signal, and then in a way that you need to only represent it as alpha sub case. OK， all right， 那我们今天上到这边，那我们下课继续。